Okay, last problem, we're going to look at a isentropic efficiency question. This time it's going to be a compressor instead of a turbine. Alright, so here we have air is compressed by an adiabatic compressor from 100 kilopascal and 12 Celsius to 800 kilopascal at a steady rate of 0.2 kilograms per second. Says if the isentropic efficiency is 0.8, determine the exit temperature of the air and the power consumed by the compressor. So if you notice in the last problem with the turbine, we were given the exit temperature, right? Or we were given enough information about the exit state of the turbine, and we use that to determine isentropic efficiency. This problem is kind of the reverse. We're given isentropic efficiency, and we're going to use that to determine the exit state of the compressor. Also, in the last problem, we were given the power, and we solved for the mass flow rate. This one's the opposite. We're given the mass flow rate, and we're solving for the power. Okay, here our system is air in a compressor. So air we treat as an idle gas. Compressor is an open system. For the conditions, we have a steady process. We have adiabatic. Also we have compressor, so delta KE and delta PE is 0. Typical conditions for the compressor. For the properties, we have the inlet pressure is 100 kilopascal. Inlet temperature is 12 degrees Celsius or 285 Kelvin. The exit pressure is 800 kilopascal. Mass flow rate is 0.2 kilograms per second. And lastly, isentropic efficiency is 0.8. Next, we're ready to start solving. So we're looking for T2, and we're also looking for the power. The power should be negative because it's a compressor, so it should be negative power consumption. Alright, so what we're going to do, just like in the last problem with isentropic efficiency, we start off by analyzing the actual device. So for the actual turbine, or sorry, no, not turbine, compressor. For the actual compressor, we can write the mass balance. For the mass balance, not of much use. We get a constant mass flow rate, but we don't have V or A for the inlet or exit. So nothing to do with the mass balance. The energy balance, we write it, then we cancel out negligible terms from the conditions, and we get work is equal to negative delta H. Since this is an idle gas in the problem, air, we can write delta H as C sub P delta T. So we get negative C sub P delta T, or just C sub P times T1 minus T2. Alright, and then for the power, we can get the power, it's equal to the mass flow rate times the work per unit mass. So once we solve the work per unit mass, we can take that and then calculate the power. Problem with solving the work per unit mass right now is that we don't have T2. So that was not a given in the problem statement. We're going to have to solve that by using the isentropic efficiency. So we don't have enough properties at state 2. We only have pressure. We'd need one other property if we were to try to get temperature from the idle gas law. So not going to be able to do it that way. We're going to have to use the isentropic efficiency to solve for T2. So let's analyze the isentropic compressor. For the isentropic compressor, we look at the energy balance and make the same assumptions we did for the actual compressor. No potential kinetic energy or heat transfer. So the work input for the isentropic compressor is negative delta H sub S, or negative C sub P delta T sub S, or we could write it as C sub P times T1S minus T2S. So T1S we know from the isentropic compressor. The way we define isentropic efficiency is that the inlet state for the isentropic device is the same as the inlet state for the actual device. So that gives us that T1S is just equal to T1, which was 285 Kelvin. Now we have to look at state 2S. So for state 2S, which is the exit condition, we know that the pressure P2S is the same as P2, and we know S2S is equal to S1. So for the idle gas problems, it's a little bit different. We don't actually have a way to look up the value of S1 in the table. Then that gives us S2S, and then we can calculate H2S and so on and so forth. So really for the idle gas problems, what we do is we can just use the fact that the pressure P2S is P2, and instead of using this, we just know that this is an isentropic process. And we know that we have an idle gas. So that allows us to use the isentropic and idle gas equations. So how would we actually use this? We could write that T2S to T1S is the same as, well, this is for the isentropic case, so we can write this as P2S divided by P1S to the power K minus 1 over K. So this is a special equation that applies only if we have an isentropic process, which we have, and an idle gas process, which we also have. So T2S is what we're looking for. T1S is the same as T1. P2S is the same as P2. P1S, since state 1, S is the same as 1, then P1S is the same as P1. So P1 was 100 kilopascal. Then we add to the power K minus 1 over K. So this will allow us to actually solve for T2S. So T2S is T1 times P2 divided by P1 to the power K minus 1 over K. So all we need to do is get the K value. Usually with this equation we would try to get the average K value between T1 and T2. We don't know T2, or in this case T2S, so we can just use the K value at T1. So let's look that up, K at T1. So T1 was, or is, 285 Kelvin. So we can go down to the specific heats. And K for air, at 285 we're going to have to interpolate here between 1.401 and 1.400. So we have 250, our value is 285, 300 was the other table value, then we add 1.401, and 1.400. So first of all, let's get K. K is going to be equal to, interpolating here, 250, 285, 300, 1.401, 1.400. So we're going to use 1.4003 as our K, and so K has no units. So that will give us a T2S value of we have T1, which is 285, times the ratio of P2 to P1, 800 divided by 100, to the power of, P2 is 800 and P1 is 100, so I was right. All that is raised to the power of K minus 1 over K. So T2S ends up being 516.4. So now we have T2S. So what can we do with T2S? Well, we can find the isentropic work, W sub S. C sub P times T1 minus T2S. So we can get a C sub P average here between T1 and T2S. C sub P at T1, that's at 285. C sub P for air at 285, we're going to need to interpolate here between 1.003 and 1.005. Keep going on the next page. 1.003, 1.005. C sub P at T2S. Also going to need to interpolate here between T2S is 516. So we're going to have to interpolate here between 1.029 and 1.040. So we're interpolating between 500, T2S is 516.4, and 550. Then we add 1.029 and 1.04. So our interpolations here for C sub P at T1, we get interpolating 250, 285, 300, 1.003 and 1.005. We get 1.0044. For C sub P at state 2S, we get, here we're interpolating 500, T2S, 550, 1.029, and 1.04. So we get 1.0326. So that gives us a C sub PS, which is the average specific heat between T1 and T2S. take C sub P at 1, C sub P at 2s, and then take the average, 1.0185. Alright, so now that gives us a work isentropic of C sub Ps times T1, 285, minus T2s. So the isentropic input work is negative 235.7. Alright, so that's the minimum input work for this compressor if it was isentropic. But we have an actual compressor, right? So what we're trying to figure out, what is the actual input work for the actual compressor? So if we look at the isentropic efficiency equation, for a compressor, we have Ws on top and W on bottom. So we just found Ws, then we can find the actual input work is going to be Ws divided by our efficiency, which was 0.8. So the actual input work is going to be isentropic work divided by the efficiency. Let me just check and make sure that was, yes, 0.8. Notice it's higher because it's not as efficient as the isentropic compressor. So it's going to be negative 294.6. Alright, so now we have isentropic work. We have the actual work. We're looking for T2, the actual exit temperature of the device. So, in this equation we found the actual work. We can use this equation to solve for actual T2. So if we have the actual work is equal to C sub P times T1 minus T2, then our T2, we'll take the work divided by C sub P. Actually, we're going to need to take T1 minus work divided by C sub P. So we're going to have to get C sub P average between T1 and T2, but we don't really know what T2 is, so we can just assume a C sub P at T1, which was 285. So here we get that T2 actual exit temperature of the compressor is T1 285 minus the actual work divided by C sub P at T1, which gives us 578. So we notice that our condition still here is true. T2 is always greater than or equal to T2s. T2s was 516 and T2 is 578. The last thing we were asked to do was to calculate the power. For the power, we just multiply the actual work times the mass flow rate. So the power is equal to mass flow rate, forgot what that was, that number is 0.2, times the actual work input. So our power here is negative 58.9 kilowatts. And it's negative because we have a compressor, meaning it's an input work input power. So that's for the compressor problem. And to finish it up, we could just sketch this out on the TS diagram. So we can put in our constant pressure lines here. One at 100, and then state 2 at 800. So we'll sketch the actual process first. Here's state 1. It had a temperature of 285 Kelvin. And state 2s, or sorry, state 2, the actual state 2 is at 800 kilopascal. Somewhere over here. We know T2 here is 578, I think. That's what we found there. Yeah, 578. For the the isentropic process, it would have looked like from 1 we go straight up to state 2s. State 2s had the lower temperature, which was 516. Alright, so this is our isentropic efficiency problem applied to a compressor. Again, the key thing is we're comparing the actual process to the isentropic process. For a compressor, the isentropic process would be the minimum input work for that compressor under its operating conditions.